Now for second law of thermodynamics. So QH can basically mean what is the amount of petrol you put in your car, right? And this goes to our engine. Okay. What the engine does is it uses the heat or energy from the hot reservoir to do some work. Okay. And whatever energy it doesn't use, it comes out on the other side, and it comes out to the lower or colder reservoir. Okay, TC, and this is the amount of, okay, it comes out at a lower reservoir. So basically your second law says that you can never have an engine which is able to convert all the energy you put into it to useful work. Okay, you'll always, in reality, you'll always have an engine where the energy that you put in, only some of that energy will be converted to work, the others will be lost at a lower reservoir. Okay, it can be lost in terms of heat energy, okay, as friction between the parts of the energy, and so on, right? Now, so when you have engines, what becomes important is finding the efficiency of that engine. Okay, and the way you find that efficiency is equal to how much of the input energy can you convert to useful work. Okay, that is what the efficiency of the engine is. How much of the input can you change to work? So your efficiency is basically your work done divided by QH, because QH is the total energy that you put into the engine. Okay. Now if you look at the work done, suppose, just the analogy, if I have suppose 10 apples here, okay, when these 10 apples goes into the engine uses 4 apples to do work. Okay, that means when it goes into the engine, 4 of the apples is used up to do the work. Okay, whatever apples are not used gets discarded down here. Okay, so if you look at that, if 10 apples goes into the engine, 4 is used, whatever left, 6 apples is discarded. Okay, so similarly, how did we end up with 6 apples? Or in case if the amount that is taken by the engine is not given, suppose it says 10 apples are put into the engine, okay, and coming out of the engine on the discarded side is 6 apples. Okay, so how many apples were taken by the engine? What you'll do is apples taken by engine is equal to 10 minus 6. So similarly, that's how the formula is derived. Your work done is equal to the amount of energy that you put into the system minus, okay, minus the heat energy that is discarded divided by QH. Okay, and that is how that formula is derived, and you'll see in your books this is usually written as, okay, if I do QH over QH minus QC over QH, okay, I can actually divide this up like this, I get 1 minus QC over QH. That's how the formula is derived. Now be very careful. I've seen some students, they say the formula is 1 minus QC over QH. Okay, this is wrong. The formula is 1 minus QC over QH separately. Okay, if you write the formula like this, then this 1, instead of 1 you need to put QH there. Okay, now this is how you find the efficiency of an engine for any engine. Okay, this formula applies to any engine, a real engine and a theoretical engine. Okay, next we have another formula which is written in terms of its temperature, and that formula usually gives the efficiency of a Carnot engine. Okay, Carnot engine simply means a theoretical engine. Okay, and Carnot engine, basically for an engine, it gives you theoretically what is the maximum efficiency that engine can have. Okay, so Carnot engine, it gives you theoretically the maximum efficiency that an engine can have. Okay, now in reality, if you make an engine, okay, you can use Carnot, the Carnot formula to find the efficiency of that engine, but in reality that engine will always have an efficiency which is lower than the Carnot efficiency. Okay, so Carnot efficiency basically gives you theoretically what is the maximum efficiency that the engine can have. Okay, and the way you find that is again that your Carnot efficiency is equal to, now it's written in terms of temperature, so the input temperature minus the discarded temperature over the input temperature. Okay, and this will give you your Carnot efficiency. Right, if you have a Carnot engine, then this part here will be equal to that one there. Okay, and if we do a similar thing to the temperature, you'll see the formula becomes 1 minus Tc over Th. Okay, looking at a question, one question is, one of the most efficient engines ever built is a coal-fired steam turbine in Ohio Valley, driving an electric generator as it operates between 1870 degrees Celsius and 430 degrees Celsius. What is the maximum theoretical efficiency? So when it says maximum theoretical efficiency, it's asking what is Carnot efficiency equal to. Okay, so you know Carnot efficiency is equal to 1 minus Tc over Th. Okay, now remember Tc and Th needs to be in Kelvin. If you use directly in degrees Celsius, your answer will be marked wrong. Okay, so you have 1 minus Tc. So always remember, when you have Tc and Th, Th will be the higher temperature. Okay, Th will be the higher temperature, Tc will always be the lower temperature. Okay, that will always be the case. Th will always be the higher temperature. So you'll have, okay, so you find your Tc in Kelvin, it's 430 plus 27, 3, you change it to Kelvin, you get what? 3, 0, carry 1, 4, 5, 6, 703 Kelvin. And similarly you find pH 1870 plus 273, you get 3, okay, 2143. So you do 703 Kelvin divided by 2143 Kelvin. Okay. So if you do that, 703 divided by 2143, okay, you get about 0.67. Okay, that is the efficiency, the Carnot efficiency. If you multiply by 100, you get your efficiency as a percentage, so it's 67%. So the theoretical efficiency says that engine is 67% efficient. That means whatever fuel we put into that engine, 67% of that fuel will be converted to doing work, and the other percentage, okay, about what, 33% will be discarded. Okay, but can you see it goes on and says the actual efficiency of that engine is 42%. Okay, so can you see there's a vast difference between the theoretical efficiency and the actual efficiency? So it says how much mechanical power does the engine deliver if it absorbs 1.4 times 10 to the power 5 joules of energy each second from the hot reservoir. So if it says absorbs, that means this is QH. Okay, that is not your work done, that is your QH. If you have to find power, power is equal to energy divided by time. Okay, and if you have to find the power of a machine, it is your work done divided by time, because you are interested in how much power that that machine can provide you. So how much work done, or how much work can the machine do for you in a particular in a given time. Okay, so it is your work done divided by time. And remember that this 1.4 is not your work done, it is your QH. If it says the engine, if it absorbs from something, okay, so absorbs will give you QH. If it says expel or discard, that is equal to your QC. So get familiar with these terms, right? Absorb, expel or discard is your QC, absorbs is your QH. So first thing what you do is you find your W, right? So you know efficiency is 42%, okay, the actual efficiency. So you know efficiency is work done divided by QH. Okay, so that would mean that your work done is equal to efficiency multiplied by QH. So if the efficiency is 42%, 42% means 42 over 100, so it would become 0.42 multiplied by 1.4 times 10 to the power 5. Okay, your work done is equal to 0.42 multiplied by 1.4, okay, power 5. You get 58,800 joules as your work done. Okay, so when you want to find your power, power is equal to work done divided by time. The time it says for each second, so it will be 58,800 joules divided by 1 second. So your power is equal to 58,800 joules per second, or joules per second is also known as what we call watts. That's how you write your power, in watts. Okay, so basically that's how you go about solving questions in Unit 12. Okay, if it says it's a Carnot efficiency, then you need to use this formula. Okay, and if you need to find the power, you need to understand it is work done divided by time, and efficiency is work done divided by QH. This is the first and the most basic formula, and the other formulas, QH minus QC over QH, is just derived from this formula. Okay, you can also have questions where work done is not given directly, and you might need to use this to actually find the work done. Okay, so something similar to this question, again from tutorial 7, it says an engine absorbs 1700 joules from a hot reservoir and expels 1200 joules to a cold reservoir in each cycle. What is the engine's efficiency? So you know QH is equal to 1700 joules, QC is equal to 1200 joules. You know efficiency is equal to 1 minus QC over QH. Okay, so you get 1 minus 1200 divided by 1700. Okay, you get about 0.29. Okay, in percentage it becomes, multiply by 100, becomes 29%. So 29% of the input energy is converted to work, right? Whereas the other 71% becomes discarded. Second part of the question says how much work is done in each cycle. So you know work done is equal to QH minus QC. So you can just use that because QH and QC is given. QH is 1700 minus 1200 joules. You get your work done. Okay, which is about what? 500 joules. So the amount of work done is equal to your 500 joules. Okay, what is the mechanical power output of the engine if each cycle lasts for 0.3 seconds? So you know power is equal to work done divided by time. So you have found the work done in the previous question. It's 500 joules divided by 0.3 seconds. Okay, so 500 divided by 0.3, you get about 1666.7 watts. Okay, so that's how you go about solving questions